So yeah, I'll be talking about this Elixir library that I made, and as Matthias said, I've done stuff like this a little bit before, taking kind of stuff from academic papers and implementing it in some language that I'm interested in. Um, and yeah, in terms of my background, in a past life, I worked at Shopify for a while. And more recently, I've been doing some consulting for precision nutrition. Um, and they've been sponsoring the development of this library, which is open source. So thank you to Precision Nutrition for that. Um, so PN, as Luke mentioned, they've been using this library in Ruby called Wongy for a while. And so it's a forward chaining inference engine. It's based on the Rete algorithm, which I think maybe in the end, Luke, you didn't even mention the Rete algorithm at all, right? So I will be getting into that a little bit. But basically, the Rete algorithm is fast, unlike Swish and maybe most other implementations of Prolog. And yeah, Wongy is implemented in pure Ruby, and the rules are written using a block-oriented DSL that is a lot like a lot of other Ruby DSLs, lots of nested blocks. And yeah, this is the original paper that the Rete algorithm was introduced in by Charles Forgy. And there's been various kind of versions of the Rete algorithm introduced over the years. Charles Forgy himself has done some proprietary work in making more optimized versions of the algorithm. And there's a company that has the rights to those. I forget the name of it off the top of my head, but if you look up the Rete algorithm, it'll probably be one of the first Google results you get. You can buy an off-the-shelf implementation of it that has Forgy's latest optimizations. But basically, oh yeah, and this is another paper by Robert B. Doornbos. Sorry, Doornbos. That's probably not even how you pronounce it. But this paper is the one, I basically found this through the Wongy documentation. This is the paper that the author of Wongy used to implement Wongy. And this paper, the main thesis of the paper, it's talking about various optimizations of the Rete algorithm, but a large portion of the paper just talks about the basic Rete algorithm, and it turns out to be probably the best, clearest explanation of the algorithm that you can find. So this is what I used as well to implement it in Elixir. Here's a few figures from the paper. So this is, a very simple kind of like, if you just want to understand Rete as a black box, then you can understand it as you give it changes to production memory. So in the terminology here, production is like the same thing as a rule. And changes to working memory, so additions or removals of WMEs, which you can just think of as facts. And what you get when you give it both of those things, so basically you're giving it rules, you're giving it facts, and then what you get out of it is changes to the set of complete matches. So it's giving you back like which rules are matching on which facts and how. Here's another kind of, just to give you a sense of the innards. Don't worry about the details here, but basically, there's kind of like an alpha network, which deals with kind of simple matching of constants. So if you have like, you know, something has color red, then the alpha network would be responsible for matching all facts that have color red. But then the beta network is responsible for matching like variables that have to match between conditions. So if you say um, like X is on Y is left of Z is color red. So not only do those aren't just distinct uh, things, they have a relationship with each other. So the beta network deals with um, kind of making sure that uh, everything is like all those variables are lined up. That's its main job. So into Elixir now. So I made this library. It's called Ruler. It is a forward chaining inference engine. Uh, it is inspired by Wang Yi, and it's based on an immutable version of the Rete algorithm. Um, it's implemented in pure Elixir, and rules are written using a macro DSL, which you'll see in a minute. So I'll just talk a little bit about the a couple of things. I feel like implementing this in Elixir the way that I did, two things kind of are you can keep in mind as I show you how the library works, uh, and also think about you can things that you might find useful to think about it as you're writing your own Elixir, especially libraries. So macros. For this library for Ruler, it meant that I could implement a pattern matching syntax that feels very familiar to anybody who uses Elixir. Um, Macros are almost never the right answer until they are. So this is just kind of a few thoughts of mine on using macros um, in any context. I think the big problem with macros is that they aren't composable. You can't. Uh, an example of this is like I'm not sure if things have changed lately, but I remember trying to write a Phoenix app that would just kind of accept all requests and then do something with all requests to a certain endpoint. Um, but it seemed like there was no way for me to actually like uh, match like in the router to write a route that would match on every HTTP verb, because Phoenix really relies on macros to you need to say like get, and get is a macro in the routing DSL. And um, so I had to kind of I had to write out all the verbs by hand, which is like maybe not the worst thing in the world, but it's it ends up being that like if there are certain things that your library exposes only through macros, then it means that um, it restricts the ways that your users can uh, do the things that they want. So my philosophy with macros is start with a really solid foundation of just functions working on data. Um, Make everything possible to do without macros. So go as far as you can just with functions and data. And then after all that, if it still looks like macros are going to be worth it, then you add like a thin layer of macros on top to give it that nice kind of polish for ergonomics. But if your users ever want to do things that the macros weren't intended for, then they still have this functional API that they can use that still works really well. So those are just my 2 cents on macros. Immutability. So I basically, working from this paper, the Rete algorithm is relies on a lot of mutation as it's originally written. So I made an immutable version of it, which makes the implementation of it was a little bit confusing at times, and each operation that you use with an immutable version of the Rete algorithm is not going to be as fast as a highly optimized implementation that uses mutation. Basically, you have the Rete algorithm has this big network of nodes, and they are being changed. So in my implementation, those changes are transformations of persistent immutable data structures. So that isn't going to be quite as fast as working directly with mutable data structures. But some things are faster. So we get snapshots for free. There's a couple nice things about this. One is you can have your engine set up with maybe thousands of rules, and you could have that potentially even generated just at compile time if you have if you assign it in Elixir to a module attribute. And then you can keep on reusing that engine, and because it's immutable, you can have different processes doing their own thing with it, and they're just making new versions of the engine, but it doesn't affect what any of the other processes are doing. You can also keep history of the state of the engine after each instruction, and it also enforces unidirectional data flow. So one of the things about Wangi is so the engine, the engine is an instance of an engine class, and you can have side effects as part of your rules. So if a rule matches, then you can have a side effect, and if you want, in those side effects, you can affect the engine directly in ways that aren't managed by the library. So when Luke showed the example of generating a new fact, that's happening in a controlled way that the library knows how to do so that nothing gets screwed up. But if you, as part of your side effects, mess with, like, if you mutate the engine that is currently running, then it becomes difficult to predict what is actually going to happen. So in Elixir, with immutable data structures, you get some invariance enforced for free there. It's great for debugging. And I'll just say, so Wangi has this thing called overlays, which are nice. We've used them before when I was working on this stuff with Hien, but they don't always do what you might expect. So it's a little bit, you need to do some work to get what you want sometimes.
James, couple of things. Could you explain to me again what was the what is the name? Rete network? Right, Rete network. I didn't quite understand what is the network and nodes part is. And then the snapshots is, I kind of understand it, but I don't completely understand. Then the overlay is a completely new thing for me here. So I'm getting kind of lost in three different things. Yeah.
I understand. Sorry, I introduced a lot of new stuff there. So you don't need to worry about the overlays. That's just a feature of Wangi that basically, so in a minute, I'll show I'll show ruler in action, and I'll show what I mean by a snapshot. And Wangi's overlays are basically a way of doing something similar.
Okay, and what was the reference to the Rete network where you said that it's a way of aligning the variables or something like that. I don't quite understand what does that mean.
So, oh, okay, yeah. So
yeah, this one.
This is Rete algorithm relies on this. I mean, it's in the classical version of it that is mutable. It's an object graph, and all these objects have references to each other, and they mutate each other, and it's divided into an alpha network and a beta network. So sometimes I might just talk about the network for all of it. But basically, I'm not going to be getting into the nitty gritty details of how it works too much, but what I was talking about like the beta network being responsible for making sure the variables line up. I think maybe maybe I'll jump ahead and I'll show you some code that might make it more clear. But basically, in this example, so here it's like the beta network is responsible for saying like, if we get a fact that is color red, the beta network is responsible for saying like this condition is not going to match for just any fact that has color red. It needs to be that this variable z needs to match from this other condition variable z. So z needs to refer to a specific value. So it might be, an ID of a user, or it might be like burger from Luke's example. So if this is Bob left of burger and then burger color red, then these two would match together. But if it's Bob left of burger and then salad color red, they don't match because this needs to be the same z here. Does that make sense?
Yeah, of course. Yeah, that makes sense. That there is a relation between C1, well, C2 and C3 in reference to Z at least.
Yeah, so that's all I meant by making sure the variables line up, and that's what the beta network is responsible for. But understanding, I mean, it's getting into the nitty gritty of the algorithm, which I'm going to stay away from for time's sake.
Yeah, and what was the alpha network for?
Sorry, the which?
What was the alpha network for?
Oh, the alpha network is for all of the simpler matching. So just basically the alpha network will match on like burger color red and salad color red and sandwich color red. And it doesn't care about the variables at all. So the alpha network does its matching of just like constant values that you're saying are explicit, like color red. It'll match anything that's color red. And then it passes those onto the beta network in a way that the beta network then can only worry about matching up the variables, more or less.
Okay.
Yeah. Okay, so demo. All right. Okay, so how's my size here?
Looks good to me.
Okay. Oops. Okay, so this is just like a project that I have for the sake of doing this demo. So I want you to imagine, so this is going to be a modified version of the Slack channel notifications thing that Luke was talking about. So imagine that you have a system where you have these different kinds of entities, and they are represented by structs. because that's a typical thing to do in Elixir. So we have users and channels and memberships and messages. The odd one out is membership, because for the sake of this example, I figured I would not give it its own ID. It just has a user ID and channel ID. So we can imagine that this is coming from some table with a composite key. But basically, everything else has its own ID. And then memberships are like a join table or something between users and messages. So I tried to make it map a little bit to something like you might have in a database. So we have, I'll just scroll down a little bit. So, these are the kind of structs that you might have. Here's Alice and Bob and Carol, and jokes channel and a secret project channel, and then some messages. And so we have these structs in Elixir, but we want to turn them into those triples that are facts. So I just have a couple. It's just a function here that that turns each struct into facts, and I'm going to let's see. Okay, so I'm just gonna show you. Let's see. Okay, I'll just start with showing what one of these rules looks like. So basically, so this is kind of a version of what you saw in Luke's talk. So here is a rule for message visibility. So rule here is a macro, and it has this particular syntax that you can think of as like a modified pattern matching syntax, similar to normal Elixir code. So basically, it's going to look for a fact where there is some variable user ID as the first element, and then the atom type, and then user here is referring to, so it's referring to this module. So in Elixir, modules are atoms, or when you refer to the name of a module, it's an atom. So when I refer to user using this alias, it's actually like the atom elixir.rulerobserver.demo.user. So that's what here. So I'm saying there is a user ID of type user, message ID type message, channel ID type channel. There is a, so the message ID that I already have selected of type message needs to have a channel ID that references the channel ID I selected. So already this is narrowing it down quite a bit. So this rule at this point is only going to be matching on, messages, but it's going to really be any message because every message is part of some channel. But the key point is that it needs to be this particular channel. So we've kind of established that for any, in this context of the rule, this needs to be the same channel ID. And then this is saying, so this any keyword is part of the syntax of the macro. And it says, basically any of these two things must be true. So it's kind of like it's like a disjunction or a Boolean or kind of. So the user ID that we've already selected must be a member of the channel that we've already selected, or the channel ID must be public. So altogether, what this is doing is it's saying, like, we're selecting all of the messages that are part of a public channel, or that the user ID that we've also selected needs to be a member of the channel. And if all of that stuff matches, then we imply a new fact. So this is like the gen keyword in Wangi, which Luke showed. So if those things are true, then we imply message ID visible to user ID, user ID. So we imply this generates a new fact. So I'll just show you kind of what that looks like.
Just a second. Can you please go back to the example earlier, or the rule earlier? Yeah. So here the message visibility rule. The message visibility mainly depends on the channel being, because every message belongs to a channel, and if the channel is public, then the message is visible irrespective of the user which it belongs to, right? Then do we need? I mean, so the rules that the message should match the user ID for a public visibility of the message is not important, right?
It's saying, like, basically a message is only visible to a user either if the message is in a public channel or if the user is in that channel.
But I think what you're getting at, Dai, is that in the case where it's public, every message will match as long as it's in a channel, which is what we want, right?
That's right. That's right. Yes. So if the channel is public, then every message will match, which means that this will create a new fact for every user. So we do then imply that every user can see the message. Does that make sense?
Right.
Okay. So I won't show it in the REPL, actually. I'm going to jump over to here. So this is a visualization tool that I created. It's still pretty rough around the edges, but you can kind of see where I'm going with it. So this is showing, at this point, this is just showing an engine that already has that one rule, and then a bunch of facts about users and channels and memberships. So that doesn't yet have the any messages in it. If I instead show, I can add a message in the instruction queue. So here we have a bunch of, can you see this zoomed in when I do this?
No.
Yeah, it is.
It's not zooming in?
It's not zooming.
Okay. All right. Does that zoom in?
Yeah.
Okay. So here we can see in the instruction queue of the engine, it's like adding a bunch of facts for this particular message. And then we can kind of step forward and see it do what it's doing. And so we can see that what you end up with is if we keep on stepping forward. So eventually that message becomes visible to all the users because it was posted to a public channel.
Sorry, the step forward, is that like going through the various possible sorry, is it going through the matches, or is it going, what is the step forward doing here?
Step forward is like it's going through each step that the engine takes internally. So, so this is basically a debugging tool, but I'm just using it to show you, like, for now, what facts are showing up. So you can see like the facts about the message appearing, and then oops. And then eventually, I'm surprised that they're out of order, but eventually they get visible to the right users. Let me set up.
You should definitely zoom in on your mad graph viz action, James.
Oh yeah. Okay.
To flex your graph viz powers for everyone.
Right. So part of this visualization is this graph viz visualization, which shows the structure of the Rete networks. So this is the alpha network, and this is the beta network, and so basically you can see how the facts end up kind of flowing through the network in a particular way, and if something isn't happening the way that you expect with the engine, then you can inspect this and see kind of where things aren't happening the way that you expect. And this is using Phoenix Live View with a GraphViz library to basically output this as SVG. Okay, I think as cool as that visualization is, I'm going to go back to the REPL to make things a little bit more clear. So there we go. Okay. So here is oh, right, that's just the rules. Oops. Oh, I did something wrong. Oh, right. So all of that scrolling by is just the the data structure that is the engine. So it's just this huge immutable value, but it ends up doing what it needs to do pretty fast. Okay, so here you can see just like the facts that are active now. And I mentioned that you can issue queries. So this is another thing that's kind of nice about the immutable data structures is the way that I implemented this query syntax is it's basically like so this is a macro again, and it's using the same kind of pattern matching syntax. And if I do this on the engine, oops. Sorry, I lost my place. So if I do,
I'm gonna call out James. I'll risk of being applied, but we're a bit over time, so
okay.
I wanted to give you the opportunity. I mean, I want you to finish, but I wanted us to like make you aware,
Gotcha.
in case you have other stuff that you wanna share.
Yeah. Okay. So basically, this is issuing queries. So I can issue a query to say like, show me all of the messages that are visible to particular users. And then this shows me those relationships. So this is similar to what Luke was showing with issuing the query in Prolog. So you can do things that way if you want. But you can also do things by making side effects. So if I modify the engine to include a different rule here. So this is basically saying it selects a bunch of things, but it relies on the visible to user ID that's generated by the previous rule. So this is kind of an example of like a chain of causality happening and rules depending on each other. So it looks at those relationships and then it selects other variables that are related to it. And then it performs some effects based on that. So it uses this callback here to notify the user. So this is just going to print something to the screen. So if I do,
I saw it output before it.
oh, did it?
Yeah, it was like for a brief moment it outputted and then garbage after, right?
I think it might be. Wow, it's really. This isn't. This is just the time it takes to print it all out. But anyway, basically, it will eventually print stuff out. So you can do both things, and I guess I'll just end it there. So basically, yeah, the library, you can find it at my GitHub. It's called Ruler. It is, as I said, still rough around the edges, but you're welcome to try it out. And if you do, I recommend you can check out the project and run mixed test and run the tests, which are, if you look in engine test, then it shows you a lot of kind of examples of different rules testing different functionality.